In this segment, we're going to talk about a kind of grab bag of ideas related to transformers and transformer language modeling, and some kind of important concepts that help you understand where some of the current research is headed. So the first thing I want to mention are neural scaling laws, which are a kind of really important driver for why transformers are probably the default model these days and why they're used so much for language modeling. So what we have here is a graph from Jared Kaplan et al.'s paper, which looks at basically a set of kind of test losses. So this is basically perplexity, but not exponentiated, so just negative log likelihood, plotted against three different x-axes: compute, dataset size, and parameters. These are all basically scale, like as the transformer gets bigger, as the data gets bigger, and compute is a kind of mix of both of these. And on the compute graph, we see that there's these many blue lines, and these are basically different transformers with different parameters that are all trained to basically with the same amount of time. And the kind of fascinating thing here is we see that we get these kind of these plots that have this very regular kind of log linear structure, where as the parameters increase, we get these very regular decreases in test loss. And what this indicates is that compared to a lot of other architectures like recurrent neural networks, where sometimes if you just like increase the number of parameters in the model, it just doesn't get any better. You've like hit a saturation point. We see that transformers scale really, really well, where if we could just make a model that's 10 or 100x bigger than we have right now, there's really good evidence that it will actually perform better as a language model, which is quite rare and didn't exist in the era of linear models. It didn't really exist for n-gram language models. It didn't exist for a lot of prior neural architectures. So this being the goal in mind, one of the challenges that prevents things from scaling is the kind of lack of compute in order to do this. And one of the big bottlenecks there is this quadratic nature of the transformer. So this has been one of the kind of headline problems in some sense of NLP, machine learning more broadly, how to address this. There are a million proposals here. This is a figure taken from Ite et al.'s survey of this stuff, which is now even a few years out of date. Just to give you an idea of the sort of flavor of one of these things, there's a model called Performers, which was from 2020, where basically rather than forming the attention matrix here, so on the left side here we have our standard computation where A equals the keys, the queries multiplied by the keys. Instead of doing that, we are instead going to multiply things in a different order. We're going to multiply the keys by the values first and kind of collapse things down along the sentence length, this L dimension, and then we're going to multiply by the query. And this is going to make things faster, and it's going to make them more memory efficient. However, it's doing a different computation, right? This A matrix requires multiplying queries and keys and then taking a softmax, and that's not what's happening on the right side here. We have a fundamentally different computation that's approximating that, and I'm not going to go into the details of the approximation, but it's doing something different. And one kind of common theme in all this work is that usually these approximations work a little bit less well. So the kind of standard transformer is just very hard to beat as a baseline by doing alternative variants. So another kind of line of things is to kind of directly go after the fact that the attention is quadratic and just try to make that not be quadratic. So Longformer is one model that devises a bunch of custom attention masking schemes that's going to make everything kind of more efficient when you want to encode very long documents. So the idea is to enable these things to scale to much larger contexts. So these basically rather than using the full n-squared attention matrix, they have this kind of combination of patterns like a sliding window pattern, this dilated sliding window pattern, and this global pattern where you're able to look at certain other tokens. And kind of combining these in clever ways, you get most of the benefits of the original transformer, but with a sparse self-attention matrix. So what this does is it actually doesn't cut down time by very much. So in the left here, we see that there's a blue line here, which is full self-attention. And this is actually like reasonably fast. There's a chunked version of longformer, which is faster, but you know, the kind of other versions of longformer are basically the same in terms of time. The real benefit comes in terms of memory. And so based on what I kind of showed, I want you to think about what the memory should look like, both for the original transformer and also for longformer as the sequence length goes up. And one final thing I'll mention is that much of the work here has been not on developing new architectures or kind of changing the math, but instead like kind of systems level things for how we can handle GPU memory and stuff more efficiently in order to scale transformers to longer context lengths. So there's a lot of other innovation that's kind of a bit outside the scope of this class that's made these things kind of get better in recent years as well. That's the end of the segment.